Hello guys, and in this video, this is the first part of the ARMIA model, in which we will, like for this first part, just mostly talk about the differencing in the stationary from the time series and how we can conduct for the transformation to just erase and smooth for the trend and the differencing of the data. So I first of all provide you some kind of a short background about the ARMIA model, or in detail that stands for the autoregressive integrated moving average. So you see that we have the three parts. The first part could be AR, that means autoregressive. You remember about that, normally for the time series, they will be impacted by the historical data of the cells. So we involve for the variable of interest for regresses to its own large values, and that's what part we will talk in the chapter, like in the later section of 8.3. The first part of the chapter is 8.1. We talk about I, that means integrated. The data values have been replaced not by itself, but the difference between the values and the previous values. That kinds of differencing process may have to perform one or even more than that. But however, the ultimate goal of that will be just try to erase for the variability in the data, and thus help for us to just better forecasting. MA, that should be the moving average, and that's what you already learned in the previous chapters of the time series, the decomposition into the part, back to the chapter number 6. But however, in this part we not talk about just the time series value itself, but the regression errors. So we use the regression error to a linear combination of the error term, and so we can use that to help to understand about the error term of the model of the regression. And like the previous one, when we already learned in the exponential smoothing, the ARMIA model is two of the most widely used in the time series forecasting. But however, they are a little bit different, and if we use together, they can be complementary for each other. The exponential smoothing is based on the description of the trend and seasonalities of the data. Why? The ARMIA model aims to describe for about the autocorrelation in the data. So for the basic and the theories about the stationary and differencing, I will leave you the time to read for this one. But however, we can shortly describe for a stationary time series would be like, it not depend on the time. You can see that they just randomly go in like a Y noise series. Y noise does mean is you run already in the previous chapters. That is something just fluctuate between or surround for mean values, but they don't change too much. Like they don't display for the trend going up or down. They also don't display for the difference in the variation of the time, right? And stationaries will be normally roughly horizontal. That means they will be just go along and fluctuates around mean, as I already tell you before. They have constant variance, and they have no pattern of predictable in the long term. To do that, we going to represent for some kinds of the difference in the stationary, and I'm going to try to demonstrate in the first part the process of the 8.1, the stationary and differencing. So first of all, I would recommend you guys to just download for the libraries, okay? The FPP2, that's the first library we want to do. The second of all, don't forget about the tidyverse. Especially in these chapters, that will be super useful for you to just shorten for your coding. And finally, library, we use another, that's a URCA. That's a new libraries, and we use that later for the unit test, on unit test. We talk about that later. Okay, so in this first part, okay, we use the data Google 200 for the demonstration. If you still remember that, and in case that you don't know, Google 200 and to check it. You see, that will be the daily closing stock price of the Google Inc. And we have the Google 200 content for the first 200 observation from, I guess, like February of 2013 into maybe 14 something. So if you're not sure about that, you can go and check it. Alright. SDR, the Google 200. This is the first 200 observation. And if you don't feel like that, just let them out, because we just had 200 observations, so it's fine. Okay, so it's a daily data of the first 200 data. Now, let's check for the probability. Don't forget about checking the probability of the residue of the data. Okay, so let's go and use for the auto plot thread. Okay, of the Google 200, and I want to see that. You see, like they store it surrounding, like I'm not sure, but 380 something or 90, and then they end up in the end of the period, like up to 530. So we have the kind of the chain, right? You have the upward trend or something like that. And I really want to check about the. I use the function check residue. If you still remember, we can use it to check for the residue of the time series. If that really look like for the white noise or not. If not, big problem. If no, that's be fine. Okay, so I'm going to use this for the Google 200 and apply for my function. Check residue. And should be the time for them to just generate for the graph. You can see easily that the residue also have a chain over time. They had the ACF, the autocorrelation function, and you see that should be autocorrelation between the current values and all the large value from 1 into maybe 25 something, right? And the residue, they are following for some kinds of the check. Alright, so that should be the point. So that should be the point. Because I can see that there kind of strong autocorrelation in the residue. And also they look like they not really follow for their normal distribution. And also they have the trend in the residue. They not white noise. So that's the problem in the data. This will be the time for me to think about another way to just modify and transform for the data to be more stationary, right? So, in this part, I use the Legend box, okay, test to check the stationarity of the time series, okay. And I want to use this for the mock test, okay. And I want to use for first of all the Google 200 data with the large values, maybe up to 10, okay. And type, I will type out will be Legend box, okay. That should be the Legend box test, and that p-value will be smaller than 0.05. So wow, look like the problem of being not a white noise time series. Okay, the p-value has slowed down. So it should be the time for me to different the data. It's not too hard. I can use for the different function, right? And then I choose the data for myself, and let's check it. This is the difference between the original data and the previous data. So you see like the difference between the first, the second will be like, look like this. And anyway, they no longer to be clearly. But however, you can see that if now I'm going to use this, and okay, why I have to do that? I want to check it by use the different. Okay, I want to use for the pipeline operation to just easy my data. So different one more time. Okay, let's look like this way, and it's available. However, now I want to use this for the box test one more time, and large equal to 10, type equal to Lejang box. Okay. And yeah, I have some kinds of like error. That's it. Maybe. Now you can see the Lejang box that has been already created, and you can see it. This would be the result, right? This will be the result. I don't know why what happened with mine. So you see over here, yeah, one more time, sorry for about the disruption, but you see over here, because of the p-value, okay, the p-value of the test was smaller than 0. Were larger than the critical values, the significant values 0.05. So the time series now is what? Stationary. This will be how we use for the different can change for the data, and it have a lot for it to just make the data is not no longer to be look like stationary. If you don't believe on that, I would just recommend you guys to just use for the auto plot. Okay, and we want to create it by use the check residue. Okay, and this will be how it looks like now. Right? This different, right? You see, like now, even the different will be no longer will be too large. They don't have to train, and also for the ACF, the autocorrelation function, they no longer effective to their large values, and the normal distribution has been clearly. So that's will be how the different thing can change and transform the data into more stationary time series. Okay, now let's go and continue for uses in another way. So they apply now like I want to do it for the different, apply the different thing and the seasonal differencing for the data. The data that I want to use right now will be 810 according to the recommendation of the book. So that's a monthly anti-diabetic drug subsidy of the Australia from 1991 into 2008. Remember, that should be the monthly data. So seasonal of that will be monthly, right? For example, January of this year, 2008, will be maybe have relationship to the Januaries of the 2007, 12 months apart, something like that. So let's go and check it and see one more time about the structure of the data. We have 204 observation, and also we use the A10. We want to display for all the data that's available from July of the 1991 into June of the 2008. Okay, now I want to auto plot it, the data a little bit to see how it look like. This will be the data look like, and I can also at the same time do it with the residues. For the A10. I want to see it. And yeah, one more time, you see like how they change and fluctuate over time. They have the seasonalities, but the variabilities had changed and become larger and larger over time. They had the strong autocorrelation and other kinds of problem of the stuff. So that should be the reason why I think like it's not so good to just use the original data for forecasting. That's the reason why I have to modify it a little bit. Now, this will be the time for us to just practice a little bit. Try to transform the data to log 10, right? We want to see it. I just go to it. So A10, and then apply for the log function. Okay. You see this will be the difference. And if with that, it's no longer original data, but it's just the log data, and this have to just stabilize for the data a little bit. Now I want to check it like if that's it really good. I will use the check residue. Okay, so even when it's a check residual data, you can still use it for the original data, like just a time series. Even when it check for the residue of the function of like a model. But anyway, this can also apply for a time series. So you can just use it to go ahead and feel it's comfortable. So now, even when I do for the log, the data a little bit different to the previous one. And it looked like they have changed for the fluctuation, the variability in the fluctuation over time. But anyway, the trend still there, the ACF still there, so I will have to still really very careful. So apply more transformation. Formation with the differencing. So one more time, but I use this for like one more and do it. Like let's just not stop with the A10 and large, but I also do it with the different. Okay, if you want to see it, let's see. Now the different has stabilized the data like one more level, and I do it, and I want to check for the residue. Actually, just use to check for the time series and to see that. Now you can see that they still have the seasonality, but they're different, right? They now still have the seasonality, but the fluctuation has stopped, and you see they no longer have the problem of autocorrelation and the function anymore. Okay, I do it, but I want to advance it. I want to apply the seasonal differencing. Okay, right. So to do that, one more time. But I use this for like the same function, but now different. I can use for the large values equal to 12. Okay, there you see it. These have been fluctuating and changing a little bit. Now if I do it, okay, for check residue, wow, really a wide noise. Okay, so that should be how I gonna just say about like if I really change and apply it for the seasonal, for the three different one compared between the original data when I do for the log transformation and use the log and then different for last one. Actually this will be here equal to last one, and when I log for the seasonality. Okay, so that's the point. Now I can combine for all the three time series if I really want to do it into all the things, including for the original data, the monthly log data and the annual chain of the log data. So I say them all here, right? I say them all here. For the first one, the sales, that should be the original data, the monthly log data with the log, and the annual chain in the log cell, that should be this one. And I apply for the auto plot. I faces. If I not faces, this look very ridiculous. Remember about that one? I just transform for you to see. I clear verify about the X level and the Y level and GG title, and you see how it looks over here. If I do it like I'm not faces, I'm not trying to separate for the 2, 3 time series, it will look very ridiculous, and I already told you. So over here, faces, I will equal it to true, and I want to separate them into the 3 different ones. You see, first of all, the cell original data, you see they have a trend upward and also variability in the fluctuation of the data. Monthly of the log cell, they had the seasonality but no longer had the trend. And with the annual change in the log cells, they really the white noise. Just notice over here, if they do it for the annual chain of the log cells, you will lose several kinds of the previous observations around like 12 first observation, because instead it should be the chain in the last 12, which they will omit for the first 12 observation for that. But anyway, we can transform the data, and in case like we have a long time series, that's very convenient and it's nothing, right? Okay, let's try for one more time. Okay, let's do it and try it one more time to just make sure that this can be clarified with you. So let's try one more time with the US and elect data, okay, and with the original data US and elect data. This will be the electricity monthly total net generation from January of 1973 into June of 2013. And you see that they will really have the seasonalities, right? Because that's the monthly data. We're pretty sure that it will repeat the same pattern again and again in the same time of the year, year by year, right? So we're gonna do it with the. I first of all want to see for the US and elect data, and the structure have up to 486 observation, and the same with the description. You can also try to take a look into that one by using for the heads of the US and elect, and it will look like this one. Start from January 1973, very close. Okay, now let's do it, and let's just plot the original data. Okay, so we use this for US and elect, and we want to apply it for the output plot function. Okay, you see this will be how it looks like. Trend a lot, and the same with the previous chapters. We see that they will have the fluctuation, the time, like seasonality, but also the fluctuation over with the upward trend. So that's the point, and this really needs for different things to just ease the time series. Okay, so I'm going to transform it. Okay, the data to log 10 and plot it. Okay, so I first of all use this for the same function. Okay, no, I'm going to UMS elect, and then I want to use it for log function. Now this will be log 10. Okay, no, sorry, this will be natural logarithm. Okay, so log just there. Okay, not log 10. And with the log function, we will see this will be the difference. Okay. Anyway, they compare to the previous one when the number is very large. Now it's much better. However, I still want to see it and multiply. Okay, look like a little bit better, but still have the trend and still have the variability a little bit. So one more time I do it, but this time I transform the data to log 10 and then seasonally different. Okay, and then plot it. So I do the same, but I log it first and then I use for the different with the last equal to 12. Okay, log function. Right, and you see this how it looks like over here, right? They haven't changed into the different with the last 12. Last it, I'm going to just plot it. Okay, and see now it's a very really look like white noise, even when I cannot sure about the fluctuation of the season of the other kind of stuff, but it's pretty sure that they quite roughly horizontal, and yeah, it looks like they will be qualified for white noise time series. Okay, and that should be the point. So now I will try to transform everything and grab them in the same graph. Okay, you have to be very careful about the different thing. So sometimes like with this one, the people they really think about like applying the at the same time the seasonal different, and then one more time for like one more last different. Okay, so the same, you can use this for the same function. The same function for US and make, and then you lock it, but not satisfied with them. You do it one more time for the different. Okay, last 12. But up until here, you still not satisfied with them. So I one more time do it for the different. One more time, and it will be changed from one more time, very strong, and I just use auto plot it. Okay, to see that will be the difference. Now it's even much better. So that's the reason why when the people sometimes run for the second order trick, and this will be my coding to just clarify and create for the plot between the 4 different time series, including for the original data. This is the original data. Okay, this would be the log data. Okay, this would be if you're not really feel comfortable with this one, I will just change it like this. So this is there seasonal different data. Okay, seasonally log different log data. Okay, actually it should be like that. And with this one, you see how they display, right? I lock it first, and then I different seasonally, and then finally I I different for one more order. So that's the point there. The data over here. So okay. Now, so I can see this. This will be all the things, including this one. Alright. I will close it. Look like it's not, cannot. But you can understand that after this one, okay, this will be all the thing including for the seasonal leads different data, log data, but then it's like plot for second order different. So I run for the log first, the seasonally is different, and then I run for second order different. So that should be the point. And I auto plot for to create for all of them, and I add for the layer of the graph. and it can show it like how the three function can look like. Okay, thank you so much. And that should be very clear that compared to the first, the second, and even the third, the AA difference log, they will be look really stationary, right? They're very wide known stationary and have no trouble with that. And this will be what I say is ready for forecasting later. However, sometimes you not feel comfortable with just do all the thing by your intuition, and you have to repeat again and again about the transformation and the different thing all the time like that. And with us, like it's really kind of like very way of time. So that would be what we want to just use for the unit root test. But first of all, we need to load the URCA library. Okay, library. I already loaded in the beginning of the chapters, but it's okay. I will one time repeat it. And URCA library has been available. Now I want to apply the what do people say, the KPSS, right? The KPSS test. For it to just clarify about the unit test, root test, right? For the US electric data. Okay, to see. Okay, so I use the US elect data, and I want to apply it for one more time for the log function. Okay, so of course until this point I feel like log is still a very good option for me. However, I'm not stay over there. I want to apply, right? I want to apply for the maybe no, I will not log it already. I will just use for KPSS function, right? Remember about that. This will be UR.KPSS function. So KPSS, that will be the what the people stand for, the Kowalski's flip, scheme, and sign. Test, that will be back to the paper of them in the 1992. But basically, they will be the way for us to check for to check there and find to check and determine the suitable differencing order we need. Okay, so let's do it. And they have the root test over here, but it's not summarized yet. And we have to go in one more time and just summarize their result. Okay. Okay, and you see over here, first of all, be very careful. You have to take a look and see, because it's over here the test statistic, or those will be what the people call the KPSS test statistic. They will equal to over here. That's right, 8.0041, and it's much larger than the 1%. Okay, significant critical value, or we can say critical values, which were the 0.739. So that means you can conclude that it's not stationary. Okay, that will be the people will feel like they can be checked for the null hypothesis, and basically that means it's not stationary when in case like it's smaller than the 1% is significant values, critical significant value, so they will be stationary. So that means need more transformation. Okay, so this one, this time I will go and run it and apply the test on the log data. Okay, to see if they will be have a different one. So ls flag, and I apply for the log data. Okay, and let's check it if that's really have the same result or not. ur.kpss. Okay, and one more. I use for summarize to summarize. And you see over here, yeah, there's one more term that's still problem. Okay, because for the value test statistic is still very large compared to the 1% of the percentage of the critical values, and that means the data is still not stationary. Okay, now let's can do it, and one more time I want to just apply it for another kinds of stuff. So this would be better for me to just run it on the summarize the test will be not that's good. Okay, so I already clarified about that one, right? Now it should be the time for us to just not we just uses that, but we can use the function and different to determine the proper number of differencing report. So they will run it until no more not stationary problem. Okay. So let's do it, and US emac. I will just one more time. Let's see it with the log function, and after I log it already, and I will check it by using the function number of different, okay, to see. So it look like it tell me that I need like one more one order, like one order different things to just erase for the data. But however, sometimes we just not like just that way to just make sure that I will use the function and s, that means the number of the seasonally difference, to determine for the proper number of the seasonally difference. Okay, so one more time I use this one, but however I use for ns, and one more. Okay, so this will be the point. This is the point. So up until now I can feel like need one order difference, right? Okay, and for this one I also need one order seasonal different. Okay, right. Yeah, that's the point. So I'm going to do it. So like apply, I will try to apply the seasonal different thing to the data file. Okay, US make elect. Okay, and then I'm gonna just use it for log, and then choose for the seasonal. Sorry, different, but the large equal to 10, right? Remember, sorry, 12, right? And I've done it already, and now one more time I want to check it. For example, for the user SBS summary, I'm gonna check it. Oh, and it looks like over here is still a little bit larger. Okay, it's a little bit larger than the 1%. 1% is critical value, so it looks like it's still not stable. I can do it one more time by just checking it on the numbers of the different, and to see that it's still needed, and it's still display one more. So that means the time series even after the seasonal difference still not stationary. Okay, so that should be the thing when we have to apply it. Like one more time, apply it with another difference, large equal to 1. Okay, and now the time for us to check it. I will check it with the KBS summarized statistic to see if like it any kind of problem. And yeah, now it look like that the test statistic had already smaller than 1% of the critical values. And if I do it and check it one more time, this should be no, I'm sorry. Of course, I apply one more. Large equal to 1. Okay. Yeah, it's 0 now. So that means it's already clear. Okay. So up until this point. Okay. So the time series has been stationary already. Okay, so that's be all the idea behind that's running for all the different things to just make our data, the time series, into stationary time series. Thank you so much.